Hello, you should be able to hear me now. I just had my microphone on mute. Does that seem to be working, everyone? Anyone hear me? Hello, hello, hello. Anything now? Also note that the broadcast doesn't necessarily stream straight away. So just try, so you want to make sure that you've clicked live on the bottom left so that you're getting a live stream of what I'm saying rather than an older recorded stream, I think. Cool. Okay, so you guys seem to be getting sound. Is it coming through live? Perfect. And can you guys see the screen all right? Okay, it shouldn't be too big a problem with the delay. At least I'll be able to talk and work on things. You guys will be able to see the code. And as long as the sound and the video are syncing, then we can more or less keep in sync with what we're doing. Okay, so I see, so it shows me that there are 11 people connected so far. Cool. Okay, we're up to 12 people. Cool. Cool. Okay. So the basic idea of what we want to do is to just run through some lab stuff. Yes, yeah, the session is recorded. I think Google Hangouts is supposed to record it automatically, and then it will automatically send it to YouTube once we're done. So we'll see if it's worth keeping a recording of this. But at the very least, it is potentially an option. So yeah. Do you mean to stream in HD on the viewing side or on the server side? Is it available, like, is it coming through okay for some of you guys at least? I can also make the font on the screen bigger, so you'll be able to see more of the code at once. No. I'm just trying to find the code that I've been working on that I would like us to go through in the session. And it will only share. Okay, let's see if we share the entire screen. Okay, let's give that a go. Okay, I don't know, can you guys actually see enough of what's on the screen? So so my ISP is with Vox Telecom, and we use Vumatel fiber. So it's a 4 meg down, 1 meg up for 200 Rand a month. It's amazing. And under the cloth is a piano. Um, nice and exciting. Oh. Okay. Ow. Ow. That hurts, Apex. That hurts. Cut me deep. Okay, so how are we doing? Are people generally okay? Yeah, I've just posted the YouTube link as well, so you guys should be able to connect. Even if you're not able to go through Hangouts, I'm sure there must be a YouTube thing that's working. I'll give you guys copies of the files that we make. But it's worth taking some notes at least and just keeping track of everything. But certainly the video will be available, as will all the code that I write as well, that you guys will be able to see. Having said that, it's a good idea to try and be able to take down some of the code as you're going, just so that you guys can try and run as well. Every now and then I will post some of the files that I'm writing, and we'll be able to work on stuff and get it all running. Okay, so let me just get rid of this. Sorry, something's going crazy on my side. So cool. Okay. Okay, so I think if you are on YouTube and it's running, just make sure that you're running from the live stream rather than the recorded one, because I think it uploads the entire stream to YouTube as we're going. So it's possible that it shows you like an older thing. But yeah, okay. So let's get going. What I'd like to do is to run over the stuff for the lab test first. And when we've got that stuff going, we want to expand this and see what we can do with complete binary trees. Okay. So sorry, I'm having a moment of. Let me put that on this side so I can see if you guys talk. Okay, so can everyone see the lab test PDF that's in front of us? Essentially, this is the test that you guys would have been writing now if it weren't for all the fun happening on campus. Okay, you can see that the original questions are very, very similar to what we were originally doing in the tree project. So so you'll see that first question talks about the traversals, and it's literally just saying perform the different in order, pre-order, post-order traversals. Okay. and with the correct output. So I'm seeing chatting. Are you guys, is everything okay? Is everything, can you hear and stuff? Okay. So if we open up some code, sorry, I'm just looking for the handout from the lab test, okay? And we'll see, I'm just going to make this font a bit bigger. You can see that this is the skeleton that I was going to give you guys. Font, just make that a bit bigger. Okay, I hope that's big enough to see on the screen. So the skeleton that I posted is pretty much the same skeleton that we worked from on the project, minus the destructors here in the tree node, which I've gotten rid of, and then I got rid of the destructor in the binary search tree as well. The insert function and kind of these first public wrapper functions are all pretty much the same as well. The insert function, you can see that's the same as what I gave the first time. The difference is that this one doesn't have that issue over here when you insert items that are the same as one that's already in the tree. Okay. So if we're looking at our insert, this is a recursive version of an insert. Okay. So you can see that the function that we've got simply says insert a node, insert value v into some given subtree, and return the root of that subtree. Okay. So this means that when you call it at the beginning, what we do is we say root is equal to insert some value at the root. And this means that if the tree is empty, it allows us to simply insert, and it means that even if the root changes, we don't have to handle any kind of special case. Okay, so that's the reason that I've got it to return every time. Sorry, I've lost my window. Where were we? There, and I've got so many windows open. Okay, let's just clean this up a bit. Okay, and we are back. Cool. Okay, so so we insert some value v, and then when we insert this value, we then go to the tree with some root, and then we simply say if the subtree is equal to null. So if there's nothing there, then it means that the tree is empty, and we're simply inserting into that tree. We create a new tree node, and we return that. And because we're setting root equal to our first insert, it means that we don't need to worry about handling anything else. Okay. Similarly, then, if we want to insert the value, if it's less than whatever's at our root, okay, then we say we must go left. And if it's greater than or equal to, then it must go right. Okay. In each case, we return the root of the subtree that we were given. Okay. So eventually, when we get down to inserting at the very end of the tree, and we're talking about a leaf, okay, then essentially you're given a null pointer. That one will go in here, and it will create the new one and return a pointer to that. And then the thing that was a leaf, or the thing where we're now inserting a child, would have called insert using one of these two functions. And so it means that, for example, if we're now creating our new item to the left of some value, it means this one will create the new item because subtree.left was null. And then once it's created the item, it returns a pointer to that. And so in the recursive call, as we return back up, we see that. Okay. And so this will correctly build the tree for us. Okay. So I'm just going to give it a minute for the video and the streaming to catch up. And then we'll just see, does anyone have any questions so far? Just ask them on, I'm trying to just figure out, let's just ask questions on IRC. Okay, so if you have any questions, ask them on IRC, and we can carry on from there. Okay, so from there, let's carry on and see what we can do. So the first question that it asks us to do is to implement our traversals. Okay, so given some input, okay, we should then get those outputs. So we've got our pre-order traversal, our in-order traversal, and our post-order traversal. Okay, so we can go to our code. We can assume that we've been given the root of our tree and that we start from here. Okay, so here we go. The pre-order traversal simply means that we have to print out first. Okay, then we need to recursively traverse left. And then we recursively traverse right. Okay, so in order to do our print statement, that's fairly straightforward. We can simply say we want to see out the subtree dot value, and we're just going to put a space after it. Okay. Cancel sign. Okay. So we end up with our print statement. We then decide, okay, we want to traverse left. So we simply do a recursive call. Pre-order traversal of subtree dot left. Similarly, we do the same thing except we go right. Right. I'm just going to. This is irritating. Okay, I'm just going to open this in Qt rather, just so that it stops yelling at me. BST. Okay, so we're back. Okay, cool. Okay, so we've got our pre-order traversal. Okay, we know that our pre-order traversal will then go print out the value, then it will traverse left, then it will traverse right, and that's simply what our definition is supposed to give us. We then need to handle the case almost like our recursive base case. So we call it an escape hatch with recursion, and it would be your base case if you're thinking about it in terms of induction. Okay, so the idea here, so I just want to keep this chat on top so I can see. So the idea here is to say, at what point does our recursion stop? At what point do we stop going down down the different items in the tree? Okay, so at that point, we obviously say if the left subtree is null, then we don't want to recurse in that direction. Okay, so we can say if subtree.left. Okay, so if the left subtree is null, then obviously we don't want to traverse in that direction, and it's the same thing with the right-hand side. Okay. So that gives us a nice way of very simply and quickly doing our traversal. Okay. In this case, what we've got is that we check for null before we go down and do the recursive call. We could also have checked for null up here and simply gone like this and said if subtree is null, return and do nothing. And that means that at the end of every kind of recursive branch that we're following, it means that we don't need to worry about getting a seg fault at this section. Okay, so I actually prefer this way of doing it because it also handles the case where our tree is actually empty, because it means then that we simply print out nothing. Okay, so we check if the subtree that we're working on is empty. If it's not empty, we print out the value, we traverse left, and then we traverse right. Okay. From here, the other questions asked us to do our in order and our post order traversals. Okay, those are fairly similar. They should look like this. Okay, so we check whether our subtree is null. We do a traversal of the left. Then we do a print out, and then we do a traversal of the right. Options, check the tick box that hides, joins left. Carl, I'm not entirely sure what your question is asking. Are you talking about in Qt? Or do you want me to get rid of this window pane over here? Is that what you're talking about? Like that? Okay, so that gives us our in-order traversal. Okay, so we can see that if our subtree is null, if we're given an empty tree, then we don't print out anything. Can you check the tick box? Okay, so I can make that bigger. I see what you mean. Just so that the what am I looking for? HTML5 flash prime messages, location shows status, the last position, timestamp. I don't actually know what I'm looking for. Hamburger menu, yeah. I don't actually see. Ah, there. Cool. Okay, so that should be hidden. So the chat thing should be a bit less busy. Okay. Cool. Okay, so we've got our in-order traversal now. We traverse left, we print out, we traverse right. Yeah, and if we're given an empty tree, we simply exit the function early and we do nothing. Okay, so if we move on from here, we can do our post-order traversal, which is pretty much the same thing. Okay, so it will look like this. We traverse left, we traverse right, and then we print out the value that we want. Okay, and again, we need to check for null. All right, so we now have, we should now have all of our traversals. If we go back to our code, if I run it now, we can go +11 and BST, and root was not declared. What have I done? BST 22. Not that one. Line 22. Root was not declared. Root. Oh. Whoops. Okay. Root equals null pointer. Okay. So I've just added in that that root variable. Okay, and everything is now right with the world again. Cool. All right, so if we go back to the question paper, we can see that we were given some sample input. So I'm going to copy that. I'm going to run the program. Okay, we can see that it's trying to run question 1.1. If I paste that in, we can see that it gives us the traversals. Okay, and we can see that the output there is 50, 30, 24, 35, 32, 61, 58, 62. Okay, so our pre-order traversal looks correct. 24, 32, 35, 50, 58, 61, 62. That's correct for our in-order traversal. And 24, 32, 35, 30, 58, 62, 61, 50 for our post-order traversal. Okay. Now, I'm just going to take a quick break from the screen capture. And I'm going to just change over to a webcam that I'm going to try and point out a piece of paper. And I'm actually going to do the traversals by hand as well, just so that we can practice. Okay, this may or may not work. But essentially what we're trying to do is we say we had a 50, we had a 30, we had a 35, we had a 61, which is bigger than 50, we have 24. Okay. That's interesting. Okay, so it's not mirroring the screen. I wonder how to do that. Okay. Otherwise, this writing is pretty useless, eh? Okay, we'll get there. Okay. Let me finish drawing the tree at least. So 24, 58, 62, 32. Okay, and those are all the numbers that we had. For some ridiculous reason, let's see. Is that? No, that's hopeless. Okay, so never mind. I will rather do one of those live scribe things again, and I'll do the traversals from there. Okay. So let's go back to the screen sharing. Okay. Cool. If I go to your tests here, actually, Dropbox lecturing, IDSA tests. You want to go to test number 2, let's say. Is the writing okay? Are you guys, because I do have some trees here. Oh, really? Okay, that's really weird. So on my side, the pictures of the writing was mirrored, so it was backwards. Okay, so let's carry on. Let me go back to that quick then. There. Okay, so given the tree that looks like this, we're then saying if we want to do our pre-order traversal, okay, the pre-order traversal, we start with 50, okay, and it means we print out the value, then we traverse left, and then we traverse right, okay? So if we've got 50, and it's left traversal, and then it's right traversal. To do the left traversal of 50, we look over here at 30. We print out the value, we go left, and then we go right, okay? To the left of 30, we have 24. It's a leaf node, we simply put it there. Then on this side over here, we're going to the right of 30, okay? So we're saying we're over here, and that would be the value, and then its left and its right, okay? It only has a left, which in this case is 32, and the right gets ignored, okay? So we visited everything on the left here. We can then say, look at the right-hand side of 50. So we get a 61. followed by its left traversal and its right traversal. Okay. To get the left of that, we see 58. It's a leaf node. We simply put it in straight away. And to get to the right, we get the 62, which is just a leaf node as well. And so it goes straight in like that. All right. If we're doing our in-order traversal, we have the same thing, except we go left first, then the value, and then right. Okay. So to go to the left of 50, we're looking at 30. So we go left, then we have 30, and then we go right. To go to the left of 30, we see we just have a leaf node, 24, and we can just write it out. When we're going to the right of 30, we have the left, we have the value, and then we have the right. When we go to the left of 35, we see 32, and then we have nothing on the other side. Okay. When we go to the right of 50, we see we go left, we have the value, and then we go right. When we go left of 61, we see a 58, and it's a leaf node. We can just put it in. And when we go right of 61, we see 62. Easy. Okay. Sorry, I'll have to try and figure out how to get the webcam to stand by itself upside down. But okay, if we're doing our post-order traversal, it's the same thing, except we go left, we go right, and then we have the value. So we're starting at 50, so we've got that value there. Okay. The left of 50, we go left, right, and then the value. Okay. To the left of 30, we see 24. So it's a leaf node, we just put it in. To the right of 30, okay, we go left, we go right, and then we have the value, which is 35. Just 35. When we go left of 35, it's a leaf node, we just put it in. There is no right child of 35. When we're looking at the right-hand side of 50, we see we go left, we go right, and then we have our value, 61. When we go to the left of 61, we see a leaf node, so we just put its value in. When we go to the right of 61, we see a leaf node, we just put it in, so we see 62. Okay, and if we compare those values to the values on our PDF, we should see that they do line up and they are the same. All right, cool. So let's go back to the screen. Camera back. Okay, so we've done question 1. That would have given us our first 15 marks. If we're looking at our min and max functions, okay, we can continue with those now. So if we go back to our code, yeah, we simply need to implement the function that gives us the minimum. We know that the minimum value of a subtree is as far left as possible. So there are 2 ways to do this. We can do this recursively, or we can do it iteratively. The min and max functions are essentially the same, except the min function goes left and the max function goes right. So let's do the min function recursively, and then we'll do the max function iteratively, and you guys can see both of those. Okay, so there are 2 questions that have just come through. The one question is, where was the root node declared? The root node is declared at the top of the BST class. The original skeleton that I had didn't have it, so I just added it in. So don't worry about that, but it would need to be there, yeah. And then the other question on why would we actually want to sort things in this order? Okay, so obviously the in-order traversal is a very useful one, because that gives us the sorted value. Okay, so the in-order traversal simply says, if we go back to the PDF, we can see that we've got an ascending version, an ascending list of all of these numbers. Okay, so the in-order traversal obviously has applications in that. Your pre-order and post-order traversal, your pre- and post-order traversals, those are useful when you're looking at things like your postfix notation, and those can be especially useful when you are parsing languages, and for example, when you type all your formulae into a calculator and it converts it into something that it knows how to work with. All right. So So there are quite a few uses, and I'll put some links up that you guys can have a look at and see why these different things are useful. Okay. Shame. You've been kicked out of the lab. Oh, okay. That's interesting. Okay. So I'm sorry to hear about that. If you, I'm sure that this video will be available afterwards, so at least you guys can watch from that. So I suppose they must be locking it down so that people don't break in and break stuff. So okay. Oh yes. Then I was also saying with these traversals, one of the particularly interesting things that's useful is, for example, if you wanted to save all of the values, if you wanted to save the current state and layout of your binary search tree, okay, then you would want to somehow write the structure of your tree down into a file somewhere, okay? So if you've said that your file gets, your tree gets written to the file, you want to write it in a way that when you add all those items back to the tree, you get the same tree as before. And what's interesting is that if you use the pre-order traversal, you get back to the same tree as you had. All right. So you can see that if you were to create a binary search tree by first adding a 50, then a 30, then a 24, then a 35, 32, 61, 58, all of that, okay, then you'll see that the tree that you get is exactly the same as the other one. All right. So let's carry on with the min functions, min and max. Okay. So if we go to min, we said that we want to go as far left as possible. Okay. So we're going to try this recursively first. We're going to say, if you're allowed to go left, then return the minimum number from the left subtree. Okay. If you're not allowed to go left, it means we're already at the minimum number. So we first say, is this minimum? So if subtree.left is not equal to the null pointer, then it means that we should be simply returning the null, the minimum value from that. Okay. So we say return min of subtree.left. All right. And so that quite happily says to us that if we can go left, it means that whatever's in the left subtree must be less than what we've currently got. And so if we get the smallest value from the left subtree, that's actually the smallest value in the current subtree as well. And so as our recursion bubbles up from that, we'll see that the minimum value will get brought to the top. All right. Otherwise, if it is null, it means we're already as far left as we can go. And so in that case, we want to be saying simply return the value that we've currently got. Okay. And so we have our base case or our escape hatch where we say we're sure that there aren't any numbers that are smaller than the current one. And on the other side, we're saying find the minimum number from the left and return that one because that must be the minimum number in total. Okay. So now just to look at some of the questions that are popping up. If you're getting the a.out permission denied, it means that you're trying to run your compiled file is sitting on a flash disk or some kind of FAT32 file system, which doesn't have an executable bit. So if you copy the a.out, if in fact copy your entire project out onto, or at least where you're compiling, onto something that's not the FAT32 file system, and then that should fix it. Then the question about ignoring the -1, that's simply because of the format of the input. So in this input, I said that you receive a list of numbers that you insert into the binary search tree, and then the -1 means that we've reached the end. Okay, so the ignoring the -1 is just because that's the structure of our input. All right. So we've got our min and our max. Okay. So we've done our min function. Okay. So if we go then to the max function, so we've said we've done this recursively for this one. For the max function, we're going to try and look at the iterative solution. So the iterative solution is starting to say, let's have a pointer to the root node, and then we're going to keep moving that pointer down as far right as we can get it until we reach the very edge of our tree. So we're going to need some kind of temporary node. So we're going to say tree node pointer called temp, and we're going to set it to the subtree. Okay, so it originally points to the root. Okay. Then what we do is we say, while we can go to the right, go to the right. If we can't go to the right, then we simply return the value of the current pointer. Okay. So while we can go to the right, so that simply means that while the right-hand pointer is not equal to null. Okay. So while we can go to the right, go to the right. Okay. And when we can no longer go to the right, temp should be pointing at the very rightmost node, and we know that that's our maximum, so we would just return temp.value. Okay. And so that then should answer that second question, our min and our max. All right. Let's do a quick test of that. If we go down to main and I tell it that we want to look at question 2, I'm going to compile. That's not what we want. Where's the terminal? Yeah. Okay, so if I compile it again and run it with the input from our question paper, okay, we can see that it gives us the correct minimum and maximum values. All right, so that does question 1.2. Okay, so the question here is, in terms of efficiency, would the recursive or iterative function be better, or doesn't it really make a difference? In this specific case, I would tend to go with the iterative solution. And that's not really because of efficiency per se. But if you think about it, every time you make a function call, we add an extra frame to the call stack. We create all the local variables for that specific stack frame or that function call. And then from there, that one will call again and again and again. Now, if you're working in something like Java, for example, or quite a few different languages, there's a limit to the maximum number of function calls that you can make. This limit is usually quite high, but if you had a tree that was, you know, a million nodes high, then you could potentially get some kind of problem where you run out of stack space. Having said that, in this case, I don't think it's a big issue, and either of the two would be fine. In general, the recursive and iterative methods for these two are doing the same thing. So in terms of complexity, if you imagine looking at the tree, and then you look at the tree, and then you say, go left, go left, go left, go left. Our complexity in terms of the number of nodes we can visit, those are the same for both of them. Okay. If you really wanted to check the efficiency, you could implement them both, run them both on some very large trees, and then see what happens. In the grand scheme of things, in this specific example, it doesn't really make a difference. Okay. Okay, so the implementation of the max function, just to go over that again quickly. So the max function, we said, is just the opposite of the min. So the min function says go left, go left, go left, go left. Okay, for the max function, we're going go right, go right, go right, go right, go right. So go as far right as we possibly can. So subtree will initially be our root. And so we set some temporary pointer and we say, okay, let that temporary pointer point to the root. Okay. We then want to say, while we can go right, while the temp.right is not equal to the null pointer. So while there is some node to the right of us, then temp must point at that node. Okay. So imagine that this is like traversing a linked list, where instead of going temp equals temp.next, we're going temp equals temp.right. Okay. And essentially, we're doing the same thing. We're traversing all the way to the very right-handmost node. When we get to that node, okay, we know we've now reached the very last one, and then we can return the value to that. Okay. Why do we use? Okay. So I'm just showing two different ways. So I wanted to show you the recursive way of doing it for the one, and the iterative way of doing it for the other. You could do a recursive solution for max as well, and you could do an iterative solution for min. I just want you guys to be able to see both of those two patterns. All right. Cool. Okay, so the next question. Yes, actually, yeah, you're correct. We could have, so the question is, why do we need a temp pointer? Okay, we could actually just have used subtree, yes, because subtree is a local variable. So doing that would have been perfectly legitimate, and it wouldn't have caused any problems. Yeah, so that's perfectly fine. Okay, let's move on to contains. Okay, the contains function, very similar to the same as the project question as well, and we simply want to say, does a certain item from the second list appear in the binary search tree? Okay, so we go to here. Again, we could do this recursively, we could do this iteratively. I'm going to do it recursively first, and then we'll see. We can give the iterative method a quick try as well. So there are a couple of different cases. We can say that if we have an empty tree, it means that we know for sure that the number we're looking for is not in that tree. Okay, so imagine, so that's our escape hatch for our recursive function. Or if you're thinking about it in terms of induction, that would be our base case. So our base case says that if the subtree is empty, so if subtree, whoopsie, is equal to null pointer, then it means that we know absolutely for sure that the value is not inside. So we can return false. Okay. From there, we have a couple of different cases. We know that we have an actual tree because subtree is not null. So we need to check whether the node that we're currently looking at has the value that we're looking for. So we want to say something along the lines of whether if subtree.value is equal to the value that we're looking for. Okay. And in that case, we know that obviously we need to return true because the tree obviously contains the value. Okay. If it's the case where it's not equal to, then we want to say, is the value we're looking for less than or greater than? So would it be going to the left or would it be going to the right? Okay. So let's say if v is less than subtree.value, then we know that we want to check whether it's in the left-hand side. Okay. And this is where our recursive call can come in. We know that the current tree only contains the item if the left subtree contains the item. Okay. So because we've got a function called contains that will tell us whether that subtree has it, we're going to call that. So we're going to say whatever value this returns will be the same value that we return. So if the value is in the left subtree, then we'll return true. And if the value is not in the left subtree, then we'll return false. Okay. And then we look at our other case, and we say, go to the right. So if the value is greater than what's at the current root, then we want to print out what's to the right. Okay. And now we can double check that every possible path through this function has a return statement. So if the subtree is null, we're okay. And we make this check before we try and dereference value. So we do it first. After that, we say there is a tree. Either the current value is equal to v, it's less than v, or it's greater than v. Those are the only three possible situations that can occur. And so we know that every possible situation is covered by this function. Okay, so that's all we need for that. Let's see, here's question, yes, I uncommented that. So if we go to, sorry, I've lost my place. Yeah, content. If we now compile, and then we can run the program with our sample input. And we see that that gives us false, true, false, 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 true. Okay. And we can check that that's correct easily enough. We can see -5 is not in the tree. 50 is definitely in the tree. 64 is not in the tree. 59 is not in the tree. 66 is not in the tree. 99 is not in the tree. And 24 is in the tree. Okay. So that's our contains function. I'm going to do another version of this. So let's call that contains 1. And let's now try this with a iterative approach. So rather than doing recursive calls all the time, we want to say, let's rather check with some kind of curve pointer, and then we're going to have a loop that iterates over as we move each way. All right. So we essentially do the same thing. So we say we've got our pointer to the root of the tree. Okay. And because it's a local copy, as was pointed out earlier, we can change it without actually affecting our screen. The main function, okay, so just to answer the main function for contains, question 3 is this. It reads in all the values, and then to create the tree. And then once the tree is created, it reads in a value, checks whether it's in the tree. Reads in a value, checks whether it's in the tree. And we'll keep doing that until it finds a -1. Okay. So let's carry on with the contains function in our iterative approach. So the first thing we want to check is, do we have the value at the current root? So if value is equal to v, if we found the value, then return true. Okay. Then we would want to say, similarly as before, if the number we're looking for is less than subtree.value, then it means we want to check left. Okay. And so the root of our tree is now subtree equals subtree.left. So we traverse to the left. And in the case where v is bigger than what's there, we go to the right. Okay. And essentially, we then want to keep repeating this until subtree is null. Okay. Or until we found the value. Okay. So we can say, while subtree is not equal to the null pointer, carry on looping. All right. So in the same way here, we checked for null. We're checking for null here as well. Okay. If we ever get to the position where subtree is now equal to null, it means that we're pointing at an empty tree. It means we've traversed all the way through and we did not find the item we were looking for. So in this case, we should return false. In these cases, we don't need to return everything because the loop will continue. And once we hit this return statement, we know that we found the item and the function finishes anyway. All right. So if I compile this program, okay, let's get the sample input again. And we see that we get false, true, false, 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 true. So we get the same output as before. Okay. Again, these two approaches both follow the exact same path through the tree. So in terms of asymptotic complexity, in terms of the analysis that we would do like that, we would say that they take the same amount of time. Okay. In terms of actual efficiency, you might find that the iterative solution is possibly you know, a nanosecond or two faster. So really, I would say in this case, it doesn't really matter, unless, again, you're worried about your stack space. So if your tree is ridiculously big, that you don't want to have 5,000 recursive function calls, that could cause a problem. All right. Finally, let's go on to the deletion function for this tree. Okay. So this question had pretty much the same thing as before. You create your tree until you see a -1, and then from there we delete each individual value, and we perform the pre-order traversal of the tree after deleting the value. If we go to the main function that I wrote for that, for question 4, you can see it constructed the tree, and then it would read in a value, remove that value from the tree, and then perform the pre-order traversal. Okay, so you don't need to worry about the main function for that. That's all done. So essentially what you needed to do was you needed to make sure that the remove function was correctly implemented. Okay, now for this function, I'm only going to do it recursively. It is possible to do it iteratively. It's just a bit of a pain. And so I prefer to focus on the recursive solution for now. Okay. So we know that when you're deleting items, we have 3 possible cases. The item can either be a leaf node, in which case you simply delete the item, and you set its parent to point to null. The item can have a single child, in which case the parent of the one we're deleting should now point to the child of the node we're deleting. And then the last case is when there are 2 children. Okay. So let's handle the case. Sorry, firstly, just to clarify, to do this recursively, we're going to follow the same pattern that we used for our recursive insert, where our remove function is defined as a function that removes the value v from the subtree and returns the root of that subtree. Okay, and that gives us an easy way to edit the parent, much the same way as what we did over here. So when we said the left of that, it means insert v into the left subtree and return the root of that subtree. That root may have changed or it may not have. Okay, so it's the exact same idea as our insert function over here, where we're saying insert must return the root that we're trying to work with, and if that root has changed, then it will get assigned to the parent. If the root has not changed, then it will still assign to the parent, but it will assign the exact same value. Okay. So let's do a quick check here. We're just going to say if subtree is equal to the null pointer, it means that that the item we're looking for is not in the tree. Okay. So the root of that empty tree is the null pointer. We then say we also need to handle our case where we're looking for the node, okay, which we'll handle in a case that's pretty much the same as the recursive function above. So I'm going to say if v is less than subtree dot value, then it means that the item we're trying to delete should be to the left. So left, the new root of the left subtree will be whatever this thing returns. Okay? And then similarly, look to the right. Okay, so that will handle the case where we need to traverse left or traverse right in order to find the item that we want. Okay, the final case here is when we have actually found the item that we want. Okay, so if it's less than, we go left. If it's greater than, we go right. And if it's neither of those two things, then it has to be equal. Okay, so in this case, we now look and we say, well, we could have the case where we have 0 children. We could have the case where we have 1 child, and we can have the case where we have 2 children. Now, so if there are no children, then it means that the left and right pointers are both null. Okay? If the left pointer is null and the right pointer is null, then it means that we're at a leaf. In this case, we want to delete subtree because we want to delete the item that we're getting rid of. And then we need to say, okay, what is the new root of the tree that originally only contained the 1 item? Okay, so it only contained that, if the subtree that we're looking at only contained that 1 leaf node, we've now deleted that leaf node, so there's nothing in that tree. It's now an empty tree. So the root that we must return should then be the null pointer. Okay, because the parent of the node that we just deleted must now point to this. Okay. If we then look at the case where there's 1 child, so let's say the left is not the null pointer and the right is the null pointer. Okay. So we're now saying that there is 1 child and we know that it's on the left. In this case, we're going to need a temporary pointer. So we're going to have a tree node pointer called temp. And that is going to point to the item, to the child node that we don't want to forget about. After that, we can delete the item that we're trying to get rid of. And once we've deleted that item, we return what we want the parent to point to. So the parent must point to this child. Right. So we point to the child so that we don't lose it when we delete. We then delete the node that we want to get rid of. And then we return the item that is the value that we're looking for. Okay. You can do the exact same thing when there is a right child. You end up doing the exact same thing. Okay. So the idea here is we now have a pointer to the right. We delete the node that we want to get rid of. And then we return a pointer to the child. We return what we want the parent to point to. Okay. And then finally, the last case is when there are 2 children. Okay. And in this case, we have, this is where our recursion really works well here. Okay. So we've said that in order to delete something that has 2 children, we take one step to the right and then go as far left as possible. Okay, so we take the minimum value from the right subtree. Okay, when we've taken the minimum value from the right subtree, we save it in the root because we know that that's a value that can replace the root that we're deleting, the value that we're deleting. Okay, so we do that, and then once we've done that, we delete that minimum value from the right-hand subtree. Okay, so we can say subtree.value is equal to the minimum value from subtree.right. Okay, so we've taken one step to the right, and then our min function goes as far left as possible. Following that, we then want to say delete that minimum value from the right-hand subtree. So we know how to delete from the right-hand subtree. We've done it over here. There. So we make our recursive call. The value we're now deleting is the minimum value that we copied up. And then we delete from the right-hand side. Oh, sorry, I think I just placed that by mistake. Okay, and we delete from the right-hand side. Okay, and that gives us a full implementation of the remove function and its in its recursive form. Okay, so let's look at the questions. Okay, so why do we return the root? Okay, it's just the way that our recursive implementation is working. Okay, there would be ways of doing it if you without returning anything, but then you would have to stop at the parent rather than at the actual node that has the value. Okay, because it's like when you delete from a linked list. In order to delete from a linked list, you have to have a pointer to the thing before the one you want to delete. Okay, it's the same thing here. In order to delete a node, you have to set that parent to point to null or to point to whatever the other thing is. Okay. The deletion implementation. Okay, so I assume you're talking about nice. For the deletion implementation, I assume you're talking about the actual algorithm. So how does the algorithm actually work? Okay, and let's have another look. I'm going to move over back to the piece of paper. Okay, so let's go back to the tree that we had here. Okay, there we go. So if we look at our different cases, if we say we're deleting a node that is a leaf node, okay, like 24, for example, we say if we delete 24 from this tree, we want 30 to be pointing to null, okay? So in this case, we call delete, just like that. And then at the same time, we need to tell its parent to point to the null value, okay? And if we look at our code, sorry, everything's backwards on my screen. But if we look at the code, we see that when there were 0 children, okay, we say delete the node that you want to get rid of. And then in our implementation, what you return is what you want the parent to point to, okay? So we're saying that the parent must now point to the null pointer, okay? Our next case says, what if there is 1 child? So let's look at deleting 30 now, okay? We need to delete, actually, let's delete 35, sorry. Okay, so we're deleting 35. So we need to traverse through the tree to get to 35. Once we're there, we see that it has 1 child, okay? We don't want to lose this child, so we say set some temp pointer that points to it, okay? We can then delete 35, and then we say we want the parent of 35 to point to this guy. Okay, and we've said that in order to get the parent to point to something, we just return that pointer from our function, from our recursive call. So if we go back to the code here, you can see you have one child and it's a left child. We get that temp pointer. We delete the item that we found. And then in order to get the parent to point to that, we return it. When you've got the right-hand side, it's exactly the same. Okay, so if we were looking at a case like this, where we have maybe if we were deleting 63, okay, and if you were deleting 62 and we had a 63, then it's this guy has a right child, and so because there's a right child, the parent must point to that. Okay, so that's how you do it when you've got one child. If we quickly look at the case then where you have two children, maybe look at this tree and let's say we have 50, 45, 42, 70, 80, 60, 65. Okay, so this is a binary search tree. Suppose you want to delete 50. Okay, we look at 50 and we see that it's got two children. Okay, what we want is, because we're talking about the binary search trees, okay, we have to maintain that specific order. Okay, and so to maintain this order, okay, it means that our in-order traversal always has to give us an ascending list. Okay, so in order to do that, there are only two items that we could possibly put here. It can either be the maximum value of the left subtree or the minimum value of the right subtree. Okay, it doesn't matter which one you take. In this one, I wanted you to use the right one just because that's what the marker would mark correct. Okay, so we take one step to the right and then we get the minimum value. So we go as far left as possible and we see a 60. We then copy that value up here. And then now that we've moved, copy this value up, we say delete the number 60 from the subtree rooted at 70. Okay, and we know how to do that. So we start here, we go left. Okay, we found 60. We see that it has one child. And then as we just discussed, okay, we take a temp pointer and then delete the item and do that. Get the parent to point to that temp. Okay. And that's exactly what happens when we do our recursive call, because our recursive call over here is saying delete that min value that we pulled up from the right-hand subtree. Okay. Cool. So that gets us to delete. Let's just put this back. I've somehow done, oh, there we go. Okay. My microphone is back. All right. So does everyone seem to have a vague understanding of how that works now? Okay, I think so that is the end of the question on remove. So if we go down, we'll see that was question 4. Again, I'd implemented the main function for you, so there's nothing exciting there. If we compile the program and then run it with the set input, okay, we see that we get 50, 30, 35, 32, 61, 58, 59, 62. Okay, so we can see that it's deleted the number 24 that was originally in the tree. Okay, after that, it tries to delete 35. It does so, and then it does the pre-order traversal again, and then after that, it deletes 50. It does so and does the pre-order traversal again. Okay, Each of those cases, the first one deletes a leaf node, the second one deletes a node with one child, and the third one deletes the node with two children. All right. Okay, so that was the delete function. And that brings us to the end of the questions on the binary search trees. Okay. So that's all the stuff on binary search trees. The next one was something that was a bit different. Okay. We were trying to say, let's look at some complete binary trees. Okay. Okay. So to answer the question that's just come through is, what are you talking about in the announcement when you mentioned how nice it is to use arrays? Okay. And that's what the second question was about. So the second question is all about complete binary trees. And those can be very nicely represented in terms of array. Okay. So if we're looking at a complete binary tree, such as this one in here on screen, we can see that we can give the first one a 0, the next one a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And because we know that the complete tree always fills up in this order, we can represent it in an array. Okay. We know that for the tree to be complete, we're never inserting somewhere in the middle, because then we would have a tree with 3 children. You can't delete from somewhere in the middle either, because then we would have a hole in the tree. Okay, so the structure of the tree always stays the same, and so this makes it really easy to represent in terms of an array. All right. So the first question said, write these 3 relevant functions. If you've got some index I, what is the index of its child on the left and its child on the right? Okay. So the child on the left, we did this in class, but the child on the left is the index times by 2 plus 1. Okay. The index on the right is the index times by 2 plus 2. All right. So if we're at 1, 1 times 2 is 2, plus 1 gives us 3. 1 times 2 is 2, plus 2 gives us 4. Same over here. 2 times 2 plus 1 is 5. 2 times 2 plus 2 is 6. Same over here. 3 times 2 plus 1 is 7. 3 times 2 plus 2 is 8. 4 times 2 plus 1 is 9. 4 times 2 plus 2 is 10. Okay. So you see that all of these indices are quite easily found. So all these first few functions wanted was to say, get an index and return the parent index, the left index, and the right index. Okay. And so that was quite easy to do. Let me pull out the skeleton. Okay, so here's the skeleton for our complete tree. Okay, this one wanted to know what is the index to the left. Okay, so it's just 2 times I plus 1. The index to the right, 2 times I plus 2. The index to the index of the parent. Okay, well, it's going to be some adjustment of that. Okay, so let's think about these. When we wanted the right, oh, sorry. If you are at the right child, okay, Then we got to that right child from the parent by saying 2 times the parent plus 2. So if we wanted to get from 8 back to 3, it would be 8 minus 2, which undoes that. And then you divide that all by 2. And that would get us back to 3. So 8 minus 2 is 6. 6 divided by 2 is 3. Easy. If you're the left child, we said we got here by 2i plus 1. So if you're at 7, you would say 7 minus 1, which undoes that bit, and then divide by 2. Okay. So we've got those two cases. Now, interestingly, what you can do is you don't have to handle these two cases separately. You can simply say I minus 1, like that, and then you divide that by 2, and you round it down. And because we do integer division in this case, rounding down is exactly what happens because it just truncates the fractional part. And so we end up with the number we want. So if you're at 8, 8 minus 1 is 7. 7 divided by 2 is 3.5. And because we truncate the last bit, we can we get back to 3. Okay. Likewise, if we're at 7, 7 minus 1 is 6. 6 divided by 2 gets us back to 3. All right. Can one use bit shifting instead of multiplying by 2? That's actually exactly what bit shifting does. Every time you shift something over by 1 bit, you multiply by 2. And if you shift it back by 1 bit, then you divide it by 2. Okay. So bit shifting would do the exact same thing, and that would be fine. Okay. But you would still need to handle the plus 1, plus 2, and the minus 1 cases like that. Okay. Okay, so that was that question. If we compile and run, C++ 11, complete. Okay, that seems to compile. If we run the program, okay, we see our output. Okay, so we see that there's one mistake here. Okay, specifically, the question wanted the parent of 0 to be minus 1. Okay, and because of the way that we've done our truncation, we ended up with 0. Because when you're at 0 and you look for its parent, 0 minus 1 is minus 1. Minus 1 divided by 2 is going to be minus a half. And when that gets truncated because of integer division, we end up rounding closer to 0. Okay, so it ends up moving towards 0. And so in this case, that top one is wrong, but you'll see that everything else is correct. Okay, just like in the sample output. So we can then just fix this one case, and we can say if I is 0, then we return minus 1. Okay. Oh, helps if I run the program. Okay, and you can see we've now fixed that issue with the parent. All right. So that one was a fairly easy 10 marks. The next question was essentially to say, does a certain index exist? So, given that we know how our complete binary tree fills up, like this, if I said I want the node at index 11 or 12 or 13, we would need to know that those indices don't exist. Okay. So we know that there are 11 items in this tree, okay, which means that there are 11 items in our vector or in our underlying array that we use. Okay. So this is actually really, really easy. You simply say return true or false, depending on whether I is strictly less than our data array dot size. Okay. Yeah, data dot size. Don't know why it's not doing auto completion for me, but nevertheless, that's correct. Okay, so we're saying there are 11 items in our tree. Okay, if we look at our tree again, does index 11 exist? No, it doesn't. Does anything bigger than that exist? No, it doesn't. Does anything less than that exist? Yes, it does, except for negative indices. Okay, so we would then also want to check that I is greater than -1. Okay, or you could say greater than or equal to 0. Same thing. Okay. Is it still streaming for everyone? Still be running for everyone. Does everyone still see the video? I'm just going to wait a bit so that it catches up with the video. Oops. Cool. Okay. Okay, as long as it's still working, then okay, cool. So everything's back. Cool. Okay, so that's our exists function. Okay, simple as that. So if we go down to main, and we tell it to use that, and we compile, and then if we run it, this will check whether things exist. Okay, and this one was quite a straightforward one. It created the tree and then says, do items exist at those indices? Okay, and you'll see that this is very straightforward. Everything is true until you get to the number of items in the tree, and then after that, all of these things are false. Okay, and so index 0 through to 3, 4 up to here works fine, and after this, we would be trying to access nodes that don't actually exist. Okay, cool. So we have exists, and that's fine. Now we get to some of the interesting questions, and we say, given that this is a binary tree of some sort, okay, we can do traversals on it. Okay, I haven't specified that this is a binary search tree, just that it is a binary tree. Okay, but now, given that we know how to get from an item to its children, can we do our traversals the same way as before? And the answer to that is yes. In fact, it's surprisingly easy. Okay, so we want to implement the 3 traversal functions. But in this one case, what I said is rather than just printing straight out to cout, what I want you to do is push each of those things to a vector. And that vector gets passed by reference. So they're all editing the same one. Okay, so if we want to do our pre-order traversal, okay, we can simply do this. A pre-order traversal says, try and print out the value you want to do. Okay, so in this case, we're not printing, we're pushing it to the back of our vector. Okay, so we do that instead of printing. Once we've visited a node, we then traverse left. Okay, And at which index do we want to be traversing from? Well, if we're going left, we want the index of the left. And if the node doesn't exist, then we simply return and do nothing. Okay? So we have a function that checks that. So if exists, the one we just wrote, okay? Let's do it this way. If it exists, then perform the traversal from that index. Okay. If the node doesn't exist, then it will simply jump out and this function won't do anything either. Okay. We can see I've made a wrapper function that creates a vector and calls your traversal function based on index 0. And then it returns that. Okay. So we can then do exactly the same thing for an in-order traversal and for a post-order traversal. Our in-order traversal, obviously we want to do the correct recursive calls. And instead of adding to the vector first, we add to the vector after we've traversed left. Okay. Then for our post-order traversal, once again, the same thing, except we traverse left, then right, and then we finally would have printed out the number. But in this case, we now save the number into a vector. All right. So those are the same traversals we know and love from our pointer-based binary search trees. Okay. And we'll see my main function for this question. Okay. It creates the tree, calls your traversal, which gets a vector, and then I print out each item in that vector. Okay. So let's give this a try. Let's just double check. It's on question 7. Yes. Okay. So if we compile and try and run, we see our different traversals. And if you compare that to the sample output in the PDF, you'll see that they are the same. Okay. I'd actually recommend drawing the tree. Bear in mind, this is not a binary search tree. It is just a binary tree. It's a complete binary tree. Okay. And one of the interesting things we note is because it's not binary search tree, because we don't have our order condition, our in-order traversal is no longer ascending. Okay. So because our in-order traversal is no longer ascending, we know that it is definitely not a binary search tree. Okay. I'd like you to think about whether the converse of that is true. Okay. If it is ascending, does it mean that we definitely have a binary search tree? Give that some thought. Try and prove it. See what you can come up with. Okay. But let's use that as our test to check whether a tree is a binary search tree or not. Okay. So the final function that we wanted was write a function that returns true or false depending on whether or not the complete tree that we've been given is a binary search tree. Okay. And the way I want you to do that is simply to look at the in-order traversal. So if we go back to our code, okay, the first thing we're going to do is perform our in-order traversal. Okay. And that function is going to return a vector containing the integers in the in-order order. Okay. And then we are assuming for now that if the in-order traversal is ascending, that gives us a binary search tree. And if it's not, then we don't have a binary search tree. Okay. And so that we can also quite easily check. Essentially what we're doing is we're saying compare every consecutive number and make sure that the next one is always slightly bigger. Okay, so we can have a loop. That loops through every index in our array, okay, in our vector. All those, we're going to start at 1, okay, because what we want to do is we want to say there are going to be that many comparisons. So if we go here, we can say at I minus 1, so is the value to the left bigger than the value on the right? Okay? And if it is, then we're going to say that that's not a binary search tree. All right. Okay. If we manage to get all the way through all of this without returning false, then it means that it is ascending. Okay, it means that the numbers are in order. Okay, and in that case, we're going to say that it is indeed a binary search tree. Okay, so that is then our isBST function. Okay, and so if we go down to the main function for question 7, you can see it does what you expect. It reads in all the values and constructs a tree. Okay, so it just puts all of the values that it reads into a vector, and then we treat that vector as a complete binary tree. And then we check whether it's complete or not, whether it's a binary search tree or not. Okay, so let's run that. Question 8. If we recompile and then run, let's copy the sample input. Okay, so we see that if we build this tree that goes 15 at the top, then for the root, then there's 12 to the left, 83 to the right, and then the left child of 12 is 54. Okay, so we can see immediately that it's not a binary search tree, it's just a complete binary tree. And so in this case, we see that we want to output false, and so we do. Okay, if we run our same system with this input, okay, you'll see true. And if you draw the binary, tree, you'll see that you have 42 as the root node. You have 20 to the left of it, 60 to the right of it. Okay, then to the left of 20 you have 10, and to the right of 20 you have 30. Okay, and if you look at that, you'll see that that it is indeed a binary search tree. All right. And that would have been the end of the test. This last question on the complete trees was quite tricky, okay? Just in the sense that it was different, okay? There wasn't anything drastically hard in it, okay? It was just a completely different way of looking at trees that you hadn't programmed before, okay? I see you guys are freaking out a little bit about how hard this would have been as a test, okay? But if you look at the marks, at the mark allocations, okay, there were 65 marks and there were 35 marks, okay, which gets us to 100%. Oh, in fact, I've opened the wrong PDF. Sorry, the PDF that I was originally giving was 75 and 25, okay? But essentially, the first 75% of what would have been the test, okay, the first 75% of this would have been your project. It would have been exactly your project, okay? And only the second 25%, okay, if I'd uploaded the right PDF, the second 25% would have actually been something completely unseen and completely difficult. Okay. So given that you guys had seen that first 75%, it wouldn't have been as disastrous as possible. Okay, I hope. But certainly these last These last few were tricky. They required a little bit of thinking, okay? But the actual programming was not hard, okay? Yeah. All right. And so that brings us to the end of this. What I would like you to do, okay, is to take this implementation of a complete tree and then see if you can implement a binary heap, okay? If you can implement a binary heap, okay, it would be a very good thing for you to do for your lab exam, yes. So a binary heap is in there. A binary heap is just a special complete binary tree with our heap condition, okay? So we can look at it if you would like. Would you guys like to look at the implementation of a binary heap, or are you going to give it a try first? Okay. Let's have a look at a binary heap then. Okay, so we know that a binary heap is just our complete binary tree. We know that when we insert in the only open space in our complete binary tree. And when we remove from the root, but we're not allowed to leave a hole. So we swap it with this item. Okay, so given some complete binary tree, if we want to insert a new item, okay, we would simply say, where is the next open space? So in this case, it's going to be at index number 11, which just happens to be the size of our vector as well. Okay, so we know where to insert. And then after that, we look at the parent of 11 and compare the two and see if they need to swap. Then we look at those two and see if they need to swap. And we keep going until we either reach the root or we decide that we don't need to swap anymore. Okay. So let's create a new project. Non-Qt++. Let's go binary heap video. Let's go DH. Okay. So I'm just going to code everything in the main one. Okay, we're going to say we have a class that's called our binary heap. Okay, and we're going to have it like that. We're going to first support all the same functions as our complete binary tree, okay, except for the traversals and isBST and those things. So what I care about are these functions here, okay, and in fact, that constructor as well. Okay? All right, so we've got all the bits that we need from our complete binary tree. We can see we can get the left and right indices given some index, and we can get the parent given some index. Okay, we can also check whether something exists. Okay, on a quick side note, we know that we're going to have to do some swapping. Okay, now in C++, there's actually a really nice function called swap. Okay, and here is an idea of what it's doing. Okay, this looks quite ugly because of all the template programming. Okay, But you can ignore all these bits. But all we do is we take the value of A and put it in the C. Then after that, we take, so if we're swapping A and B, we take the value of A and put it in some temporary variable. We then take the value of B and put that in A. And then we take the value from our temporary variable and put it in B. Yes, yeah, I'll give you guys this code. Okay. So you can see that the swap function simply does those three operations for us. Okay, and we can call it just like this, where we can swap two items just like that. Okay, so we're going to use that instead of coding all our own swaps, which is just going to make this a bit easier. So let's look at our insert function. Okay, so our insert function doesn't need to return anything, and it's going to take some value. Okay, let's go back to our picture. We're saying, given some binary heap, the only place we're allowed to insert is over here. Okay, in index number 11. Okay, and we know to use index number 11 because there are 11 items already in our array. Okay, so all we're doing is saying how many items are in the array, where is the next open space, what is that index. Okay, so we're going to say we've got some new index, and that's simply going to be the number of items in our array. Okay, and then it's going to be -1 because we start counting from 0, and then +1 because we want the next open space. Okay, so it's just going to be data.size. Just convince yourselves of that, draw some pictures and think about what those indices will be. Okay, so we know where we're going to be inserting. We can then say data dot pushback of that item. Okay, we know that this index will always be at the back of our vector, so we just push to the back of the vector continually. Okay, so we've got the index of the item we inserted, and we insert into our vector. Okay, our vector will handle any reallocations or anything like that that needs to happen. We're happy that we can just push to the back of it. So that's easy. Okay, so if we go back to our picture, we can see that we've now added an item over here. Okay, let's go to, where was it? Lab test 2, handout, images, tree. Okay, here is the image. I'm just going to open it in a Photoshop type thing so that we can edit it. Okay, so say we're inserting the number -1. Okay, so I actually don't even. Oh, okay, that's way too thick. Let's do this. Oh, yuck! No. We want a really thin brush. Nope, this is not working. Okay, but nevertheless, so we would now have inserted our new item over here. Okay, so we would have inserted the item there. Okay, now that this has been inserted, we then compare it to its parent. Okay, and we decide, are we doing a min binary heap or a max binary heap? Okay, let's say we're doing a max binary heap. So we're saying the maximum number must float up to the top. Okay, so we then say compare the item with its parent. If the item is bigger than its parent, then the two must swap. Okay. So if the item we've just inserted is bigger than its parent, okay, then we must swap those two items. Okay, I'm maybe going to just pull this into a separate variable, just so that it's easier to see. Okay, so we get the index of the item's parent. We then compare it with its parent. If the item is bigger than its parent, then those two must swap. Okay. Then what we say is we could potentially have to do that a couple of times. Okay. So this entire thing has to sit inside a loop. All right. Let's maybe say, let's do it like this. Let's say parent equals that. While that is true, swap the two items. Say that the new index is now equal to the index of its parent, and parent is equal to the parent of that index. Okay, let's think carefully about what that means. If we look at our picture again, we've got 11 and we've got its parent. So we've got index 11 and index 5. So parent points here and new index points there. If we swap these items, it means they were in the incorrect order. Okay, so whatever was at index 5 is now in index 11, and our new item is now in index 5. We then need to compare the new item that we've just inserted with its parent. Okay, so we now say that parent is equal to this one, and our new index is now sitting over there. Our new item that we inserted is sitting there, and its index is whatever the index of the parent was originally. Okay, that maybe looks a little complicated. Just try it and you'll see what happens. Okay, if our insert doesn't perform a swap, okay, if we don't need to perform a swap, then it would mean that the item that we inserted, okay, so if the new item and whatever its parent was don't need to be swapped, it means that this item here is less than the parent. And because that parent is less than its parent and its parent and its parent, we know that as soon as we don't have to do a swap, that everything is okay. All right. So we don't have to do anything. We don't have to do anything fancy over here. Yes. Can't use GIMP to save my life. Close enough though. Okay, so we now have our insert code. Okay, and that should, I hope, insert the item that we need. Okay, so let's have a look. We are going to say, I'm just going to put in a little print statement here saying swapping data at new index with data at parent. All right. So that's just going to give us a little bit of debugging output. And then over here, in our main function, let's say we're going to have some vector to start with. And let's say we've got, okay, please draw this complete binary tree as we talk. Let's go with a 42, which is our first item, and that will be the root. To the left of 42, we have to have a number that's smaller. Okay, so let's just say 38. And to the right of 42, we're going to have 30. Then to the left of 38, we're going to have 37. And to the right of 38, we're going to have, let's say, 28. Okay? So that gives us a binary heap. All right? So we can then say, let's create a binary heap. Binary heap B, and we're going to give it that vector. Okay. From there, let's do an insert and see what kind of printouts we get from this. Okay. So if we go b.insert and let's insert a value that is smaller than 30. Okay. So in this case, we shouldn't have to do any swaps. All right. So if we insert the value 25, okay, we should see that that no swaps happen. Okay. If I run this, we need a public right at the very top. Okay. Cool. Okay. We can see that we don't have any fancy printouts. Okay. Which means that we never went inside the swapping loop. Okay. If rather than inserting 25, we insert 35, okay, so it means that to the left of 30, okay, in that only open space, we insert 35. We should then say that 35 is bigger than its parent, and so those two values should swap, okay? Then 35 is less than 42, so nothing should change from there, okay? So we expect to see one swap. And it should say swapping 35 with 30. Okay, and thankfully, that's what we see. Okay, easy. If we put in something that's bigger than 42, so let's say 84, okay, 84 gets inserted to the left-hand side of 30 because that's the only open space we've got. Then we say that 84 is bigger than 30, and so those two should swap. Once that's happened, 84 is compared to 42, and 84 is bigger, and so those two should swap, okay? Once they're at the root, okay, we should hopefully be finished, okay? So we should see that our program crashes, all right? And so the problem there is that, remember, the parent of the root is -1. So we're trying to access our index at -1, which is obviously a problem. Okay. But up until that point, things seem to work okay. So we inserted our 84. We then see that 84 swapped with 30. After that, 84 swapped with 42. And then it tried to compare 84 and the thing in the thing before that. Okay. Which interestingly didn't crash straight away. Our vector at -1, that memory evidently belongs to us. But when you try to do the actual swap, then we have the problem. Okay. So what do we need to do? We need to put in some kind of check that just makes sure that we're not trying to access -1. So let's check first. So we check that the parent is not -1. Or we could check that new index is not 0. Okay? Either of those two things will check the same. Right. So we check that we're not at the root. If we are at the root, we jump out. Okay? If we aren't at the root, then we check whether the two things need to swap. And if they do need to swap, we perform the swap and then continue checking again. Okay. And so in this case, you see it does exactly what we want it to. Okay, does that all seem to make sense? Okay, now there's only one other function that our binary heap must support. Okay, so we've just said that the binary heap can give you the maximum number, and that we can do that efficiently. So you're only ever allowed to get the max number from our binary heap. And so we know that that will always be at the root. Okay, so let's do this. Let's say int pop max. Let's call it. Okay. And then from here, we need to think about what do we need to do. Okay, so we need to say, save the number somewhere so that we don't lose it. Okay, so let's get an int, and we're going to call that output. And we know that the root is always at data location 0. Okay, so we've got the item that we want to return. Okay. From there, our algorithm to remove from a binary heap simply says that you take the last item that was inserted, okay, you copy that to the root, okay, copy or move, either of the two, okay. So we copy that to the root. So we say that data at 0 is equal to the very last item in our vector. Okay. Now, lucky for us, vector has a function that tells us that, right? Data dot back. Okay. So that will give us the last item in our vector. Okay. Now we can also remove that item from the vector because it's no longer necessary. Okay. So we can pop off the item. Okay. So we copied out our root, we copied the last inserted item over the root, and then we removed that last inserted item from the vector. Okay, so if you're looking at the picture of the tree that we had from this, okay, we had a 42, and to the left of that was 38, to the right of 42 was 30, to the left of 38 was 37, and to the right of 38 was 28. So the very last item in our complete binary tree is 28. Easy. So we say copy 28 over the root, and then remove 28 from the vector. So essentially, this is what's happened to our vector. Okay. From there, if you've drawn the tree, so you cross out your 42 and you now have a 28, you now say compare 28 to its children. Okay, and you say, are either of its children bigger than that value? And if they are, we need to swap. Okay, and we keep doing that all the way down to the bottom. Okay, so this is quite easy to do. Okay, yes. So Sandmaster, yeah, that's absolutely fine. If you say data at size -1, that would also give you the last item. So you could also do this. Okay, and inside the vector, that's exactly what it is doing. Okay, so so it's doing the exact same thing. Okay, cool. So we've now done that. We now need to start saying, while some important condition is true, we need to keep swapping with children. Okay, so we compare, or maybe let's get some integer for co. Okay, that is the index of the item of our 28, for example. Okay, so we've moved it to the root, and then that is the index that we need to compare the node at that index with its children. Okay, so we need to compare the root with its children, and then cur will update accordingly. Okay, so we now say, let's get the maximum, or let's get the index of the left child. So let's say left is equal to idx left of cur. Okay, and int right is equal to idx right of cur. Okay. Then maybe another thing is that we can say, let's get the let's figure out which of those two is the maximum. Okay, so if data at left is bigger than data at right, okay, then we need to compare our root with the left child. With the left child. Okay, if that's not true, then we need to compare it with the right child. Okay. Easy. Okay. So we then say, if data at cur is less than data at left. Okay. So if the child is bigger than the node we're currently looking at, then those two items need to swap. Okay? So swap data at cur and data at left. Okay. And then now we need to check whether now we follow it down and we go to the left child. Okay. So we say cur equals left, and our loop would continue. Similarly, if the right-hand side was the bigger one, then we would look to the right. Okay? Like that. Okay? And we would swap like that. I just want to double check I haven't made any mistakes there. Yes, that seems okay. Now, there's another thing to think about. How long do we loop for? We either loop until 28 gets down to the bottom of the tree, or we loop until 28 no longer needs to get swapped. Okay, so if it gets to a point where its children are indeed smaller than it. Okay, so what we're going to say, I'm trying to think of the easiest way to do this. Let's have a flag. Okay, and we're going to say some Boolean flag, and let's say that is going to be called did swap. Okay, or rather, let's start it off as true. And we're going to say, while we did a swap, okay, then continue looping. When we get to a point where we no longer need to do a swap, okay, then our loop can finish. All right. So while we are still swapping with children, okay, keep on looping. If we get to an iteration where we no longer need to swap, it means we completely finished and that loop can finish. All right. Then there's one other thing, okay, that maybe we haven't talked about, and that's what happens if we swap all the way down to a leaf, okay? And now it's at a leaf, okay? And maybe we can't look at its right child, okay? So we need to think about that as well. Because in this case, if, for example, if it doesn't have a left and right child, then when we go data at left, data at right, okay, we're actually going to have we could have a segfault, or if the vector has allocated memory for us, we're just going to make a mistake and break the world. Okay, So luckily for us, we have an exists function. Okay, and that checks that these are indeed valid indices. Okay, so let's think about this. We want to say if the left-hand side is that, if the right-hand side it has two children, then you compare left and right. If it has only a left child, then you only look at that with the left. Okay, so let's put an if statement above, and then we'll see if we can simplify things a little bit afterwards. Okay, so if the left child does exist, okay, then maybe and if the right child exists. Yeah. Let's put that there. Okay, so I've just said first check that both of those children exist. All right. If they both exist, you take the maximum of the two and you compare cur with that. Okay. If only one of them exists, okay, then it will always be the left-hand side. Okay. So else if, yeah, so if the left-hand side exists, then we simply compare it to the left. Okay. Otherwise, if the left child doesn't exist, then we know for sure that the right-hand child doesn't exist. Okay, because it's a complete binary tree. Okay, but if there are no children, then we actually don't need to compare it to anything. Okay, so else our loop can finish. Okay, let's swap this false. Okay, let's take a moment to just review this. We swap our value to the root. We remove it. Cur is less than naught. Did swap is true. We enter our loop. Left is equal to the left index. Right is equal to the right index. If the left index exists, then and the right index exists, then compare the two and swap, look and see whether you need to swap cur with the maximum of those two. Otherwise, if the right doesn't exist, okay, so if this whole thing is not true, it either means the right doesn't exist or it means that both don't exist. Okay, so then we check, does it mean that only the right doesn't exist, in which case we do that swap. Otherwise, we say that we are finished. Okay. Let's run this and see what happens. I would like to say, let's do e.popmax. Okay, and let's put in our debugging line again. Yeah, this is the percolation. Yeah, so all of these swaps are percolating down. Otherwise, you can percolate up as well. Okay. So we say C out. Oh, in fact, let's just do this. Okay, so we're swapping cur and left. All right. Otherwise, down here, we're swapping cur and right. Okay. And otherwise, down here, we'd be swapping cur and left again. Okay. So we can now run this. let's just go back to the original one. So we had 42, and then we had 28 over there. Okay, so we compile, and I'm running the wrong program. I'm just going to run this. Okay. Oh, yes. Okay. We saved the output, but I didn't actually return it. Okay. So at the end of this function, let's return output like that. Okay, that should now give us some working stuff. Yeah. Okay. Yes, it will. I will. This will be on YouTube. Yeah. Okay. So we remove item 42. Okay. So again, draw this, or maybe. Okay, I'm actually going to go back to the webcam quick on the piece of paper. Okay, so we have our. Sorry. Okay, we are back. So we said that our tree looked like this. 42, 38, 30. 37, 28. Okay. So we then say, if we are removing the max item, which was 42 at the root, okay, we say take 28 and put it up here. And delete 28 there. Easy. We then say, compare 28 with its maximum child, okay, which is 38. Do they need to swap? Yes, they do. Okay, so we perform a swap. So 38 goes there, 28 goes there. Okay. We then compare 28 with its two children. Okay. In this case, it actually only has one child. So we only compare it with the left one, and we say, do they need to swap? We say, yes, they do. Okay, because 37 is greater than 28. And so we perform another swap. 37 moves over there, and 28 is now down there. Okay, so you can see we did two swaps. We swapped 28 and 38, and then we swapped 28 and 37. Okay, and if we go to our the output of our program, we can see that that's what we see. That's what we get. All right. Okay, so that is our implementation of a binary heap. Okay, this set of if statements and that we could probably do a bit more elegantly. If you give me one sec, let me think about it. If you say no. Okay, I think I'm going to leave it like this, but I will, when I upload the code, I'll see if there's a if I can condense this a bit into something a little bit more readable. Okay, but essentially that gives us the full implementation of a binary heap, of a max binary heap. A min binary heap would then be exactly the same, except that when we insert and compare to the parent, this inequality would swap around. And when we delete and compare with the children, we would be looking for the minimum of these two. Okay. And then we would check that cur is greater than one of the children, which would be the case when we want to swap. Okay. So that brings us to the end of the implementation of a binary heap. yeah, I think that's pretty much everything I wanted to cover. Are there any other questions? Everything will be on YouTube and Moodle, and I'll post all the code and all of that. Thanks for sticking around and all of that. I know it's been a very long video, so I'm sure some of it, some of it you'd have been clicking that board button. But yeah, I hope this has helped, and I hope that it's covered what we need to do. The question, can we do this on Monday? Yes, okay, we can. We can do this on Monday. But we do have another section that we need to finish on sorting. Sorting is the very last section that we've got. Okay. So the last, sorry, one sec. Cool, and we're back. So the very last section is on sorting. We'll be looking at the merge sort, the quick sort, which are the two recursive ones that we'll be interested in doing. We'll also be looking at bubble sort, insertion sort, and selection sort. And we have done, we've already done AVL sort and heap sort. Okay, so the heap sort is just put everything in a heap, remove everything from the heap. The AVL sort is put everything in the AVL tree, do the in-order traversal of the AVL tree. Okay, and both of those gave us n log n time. All right, so we're going to see that if we do a bubble sort, a merge sort, a bubble sort, an insertion sort, a selection sort, we end up with n squared time. And with our merge sort and quick sort, we'll see that generally we end up with n log n. Okay, and so we do need to cover that. It is in the exam. So for Monday, we'll leave it at this, that we will, assuming the Monday lecture goes okay, then we will do sorting first. We'll do an example of the binary heap stuff first, and then after we finish the binary heap stuff, we'll start on sorting. If we get interrupted, if people are still protesting and going a bit crazy, then we'll probably have to do one of these videos again. If we don't get interrupted, then we can hopefully finish sorting by the end of Monday. And then that means we'll have one last lecture after that, which is the 26th, okay, which we can use for revision and general stuff. Otherwise, if we do get interrupted, then we'll go through the, we'll make sure that we go over sorting on that as well. Okay. Yeah, so I hope this has been helpful, and enjoy the rest of your evenings. Have a good one.